I would tell little bit why this system SR-RU206, it's electronic and magnetic ground state, and why it is interesting. Actually, this talk is about electronic transport in this system, but I would say why we started to work on this system, because it is basically an antiferromagnetic on a honeycomb, and with a heavy atom RU with large spin orbit coupling. So this was the interest to make this system. So we made this. This system is not very heavily explored, I would say. There are few papers on theory and experiment, and which is in a sense good that it is a quiet life then. And so we made this system by hydrothermal route, and I would show you the results of synthesis and characterization and electronic transport, which kept us stuck for some reason, which I would discuss. And I would also show the effect of stoichiometry and morphology on the transport. And so basically this is the main thing. I would be talking about the conduction mechanism in this system. And I would also show the experimental realization of 2D sheets of this system. So this is an antiferromagnet on a honeycomb, separated by, so you have this RuO planes, which are separated by SR layers. So magnetism and conduction lies in this plane, which is consisting of Ru and O. And this system is hard to synthesize. You basically require high pressure synthesis for that, and it's very difficult to make a single crystal out of it. And you have this edge sharing RuO6 layers separated by SR layers. It's a G-type antiferromagnet. So this is like a graphene-like magnet. You have this, instead of carbon atom, you have this magnetic atom. So this audience doesn't need this introduction that why this system could be interesting and why it could be a possible candidate for quantum spin liquid state. And even if away from QSL, you have interesting magnonic bands which are linear, which show linear dispersion and so on. And strain-induced topological phase is also predicted by DFT calculations for this system.
You can explain that then.
So I would bring your attention to this. This system is hard to synthesize, and you have microcrystals of this system which are cold pressed. So you have transport data on the cold pressed pellet of such microcrystals, which I will show you in a while. So the microcrystal looks like this, and even on a single microcrystal, people have done transport, and this is a semi-conducting like behavior, basically activated transport with some feature near low temperature, which is because basically, as I said, that the conduction is because of RuO planes, and you have like both itinerant and localized character of electrons, in a sense that electron can hop within this RuO hexagon, and it can also travel, which gives its conductivity, and it is known to be a p-type semiconductor through DFT calculation, and that is what even experiments are showing, with a very interesting thing, that it is DFT says that it is a p-type semiconductor, in which depending on whether you include SOC or not, or include magnetism or not, band gap varies from 4 to 500 milli-electron volts to 2 electron volts, as in different papers. But all experimentalists, though there are very few reports, all experimentalists find band gap from the Arrhenius fitting to be of the order of 30 to 40 milli-electron volts, which is significantly lower than theoretically predicted value. So that is one thing which we were thinking about, that why this, what could be the reason. And second, that this low temperature, actually what is the conduction mechanism below 200 K itself is an open question. Before we started to work on this material. So this is what we made using hydrothermal synthesis. So these are micron size big microcrystals with regular shape and so on. One thing which I would just say that RU disorder is a possibility which is inherent to the synthesis route. Even the first group who reported this compound way back in 2015, there is this little 2 to 5% of RuO2 impurity, which basically comes from the precipitation of Ru metal, which turns into Ru oxide. Nevertheless, in whatever way, RU disorder is a possibility. I would like to keep that in mind. So we could then make by variation in the synthesis parameters, we synthesized these compound, and we also found that the band gap derived from Arrhenius fitting. First of all, Arrhenius fitting is in a very limited temperature range, near room temperature, just 30 to 40 Kelvin range, and the band gap is again 30 to 40 millielectron volts. So we, as I said, that we found this semiconducting like behavior, and Arrhenius fits to a very small temperature window, 200 to 300, and so we made RU rich, RU deficient, and we also played with the morphology, the grain size and grain boundary density. So even though this system is very interesting magnetically, but one has to understand that why conductivity is in this fashion. So we found that RU disorder plays a very prominent role. This below 50K,
of course, there has to go many iterations.
There are variations and change of slope and all. Nevertheless, only in this region Arrhenius fits, and even though by variation of grain size, extrinsic and intrinsic defects, basically you can push in defects and make your conductivity very low, resistance very high, and even such few orders of magnitude high, the band gap remains still low. It is between 50 to 100 millielectron volts. So this was the question we were trying to address. This is one question which we were trying to address. And second is, what is the conduction mechanism in the low temperature region? So in those who work in the field of oxides, variable range hopping mechanism is the second best thing after Arrhenius. If you have this semiconducting type of behavior or activated transport, like either way. So we tried variable range hopping. Since you have this RuO2 planes in which conduction is limited to RuO2 planes, so we tried 2D, 3D, and we found that Arrhenius as well as VRH or modified VRH, they all fit very well in the high temperature. They fit with equal goodness of fit. It is somewhat this problem of spin glass, where various models will fit to your experimental data, and it's very hard to figure out that which is the best model. So, and then second thing is that typically you find this crossover from Arrhenius to the variable range hopping at the lower temperature region, rightly so, when defects and all play a more prominent role. So you find this crossover, but in our case we found that in the same region all these models fit with equal goodness of fit. And so this brought us to a relatively lesser known model. This is called fluctuation induced tunneling conductance. So here thermal fluctuations basically modulate the barrier height, and this is a lesser known model by Ping Sheng way back in 1980. It is basically meant for mesoscopic conducting grains with insulating surface layer. So you have this tunneling, and when your size is mesoscopic range, this is basically RC network. So that is how the size comes into the picture, and a single fluctuating tunnel junction can be good enough for randomly fluctuating tunnel junction. That was the gist of the Ping Sheng's paper. And so through all the simplifications, this form of conductivity is expected from this model. And not only for mesoscopic conducting grains with insulating surface layer, this model seems to describe this highly disordered semiconductors very well, where VRH and Arrhenius do not fit. This model seems to work very well. So conducting carbon spheres, tunnel junctions of conducting material with silicon oxide coating and so on. All these spaces, this model works. And then this model so now we focus on one sample. So as I said that we synthesize sample because we suspected that disorder is playing a part. So we synthesize samples with various grain size variation, grain boundary density variation, are you rich, are you poor, and such kind of a things. Nevertheless, the result was still the same. So we focused on one sample which was morphology wise very similar to the one reported by Hille, who synthesized this compound for the first time. So we chose that sample, and that is sample A1, and only in that sample I am showing you the fitting of conductivity as a function of temperature, where all these models fit to a limited range, but FIT fits right from 300 Kelvin to 50 Kelvin. It's a good fit in the same sample. So, I already told that this model was developed for mesoscopic conducting particles, but it works well for a disordered semiconductor, which is most likely the case of our SR-RU206, which is a P-type semiconductor with low band gap, as we find, and disorder is possible. So why this thermal fluctuation induced tunneling conductors, where thermal fluctuations basically modulate the potential barrier height and tunneling happens. So why this could be suitable for the pressed pellet of SR-RU26, in which each of this pellet is a P-type semiconductor. So in such a situation, like in disordered semiconductor, basically you have two scenarios, like you have a conducting grain, and then there is a barrier before it meets another grain, and there can be a tunneling. So this is inter-grain tunneling, grain to grain tunneling. Another possible mechanism which the way it fitted so well in the entire temperature range. So if you look into the crystallographic structure, basically you have these RU-O, RU plane. So DFT calculations suggest that near the Fermi level it is RU and O levels which are near the Fermi level, and SR levels are 15 electron volts away from the Fermi level. So basically the player is RU and O, and these planes are separated, these RUO planes are separated by insulating SR layers, so as to say. So then whether tunneling can happen through these SR layers. So to do this, from our parameters which we derived from the fitting, we tried to get some estimate of the number. So taking free electron approximation is a first approximation. It could not be free electron mass, but as I said that in all other dirty systems of disordered semiconductor and as well as this mesoscopic conducting grains, starting with free electron mass, people could, and estimating the width of the potential barrier will be this distance, the width of the insulating layer, and the height of potential barrier. One could calculate, one could estimate reasonable parameters. In our case, the reasonable parameter could be, if we consider tunneling from these RuO2 planes through these insulating SR layers, then we took the crystallographic data. So we took W as 5 angstrom and free electron mass, and then we got reasonable potential height, V0 we got reasonable, and we did it for all other systems which we did. So this told us that we have both the possibility, the inter and intra-grain conduction, but for this possibility is a interesting one, because then each of your, if this happens, if thermal fluctuation induced tunneling conductance is really valid, then in each single grain you have basically a conducting layer separated by insulating layer. So you have a kind of a tunnel junction, you should get MR. What you would need in this case is out of plane. So the Z axis, when you see the hexagon, So from the C axis, if you do out of plane conductivity measurements, you should find this implications of FIT. So we tried making single crystal, we couldn't succeed in collaboration, though we couldn't make large single crystal, but now we are trying to make out of plane conductivity measurements on this individual crystallite, which is hard to make because this requires high pressure synthesis. So, so that is the conclusion of the first part. We found that Arrhenius and variable range hopping, all its variants, all the variants of the variable range hopping fit equally well in the similar temperature range. Band gap derived from Arrhenius model remains significantly lower than theoretically predicted value, and now we kind of realize that this is a system where multiple conduction mechanisms are likely to coexist. You may have transition from valence band to conduction band. You may have lot of defect levels near the Fermi level which perhaps enable hopping, but most prominent seems to be the most prominent mechanisms from our analysis seems to be fluctuation induced tunneling conductance, and this gives us a possibility that this could be a very interesting sample from its electronic point of view. It could be very interesting sample if we have this measurement on a single crystallite, and I wouldn't give you bore you with all the gory details, but it appears to us that below 50 Kelvin it has to do with antiferromagnetic correlations and all the things which are touted for this system, like both localized and itinerant character of electrons, which gives you this benzene ring like conduction where electron can just be localized within one RU hexagon, or it can travel also. So this kind of possibility. So whether below 50 Kelvin where even FIT does not seem to fit, RU disorder seems to play a very prominent role, and we need to have magnetoresistance measurement to understand the effect of antiferromagnetic correlations on the transport. So that is still remaining, but at least we have come from the understanding between 200 to 300 Kelvin. We have now come down to 50 Kelvin where we think that fluctuation induced tunneling seems a very plausible model. With this I come to the 2D version, since very happy to have Yogesh here in the audience because he provides this Na2RO3 and RuCl3 single crystal, which are the famous Kitaev candidates, and so you know that it is the 3D version which basically in magnetization and in magnetization you see antiferromagnetic transition, though these are all possible QSL candidate from indirect measurements, but this 3D antiferromagnetic correlation kill the Kitaev physics. So the idea was to exfoliate and get 2D sheets of such material, out of which only RuCl3 is van der Waals, and both Na2RO3 and SrRu26 are non-van der Waals, out of which Na2RO3 is hardest to exfoliate. SrRu26 indeed quasi two dimensional, because even though it is not van der Waals, but out of plane interaction along the C axis are weak. It is very easy to exfoliate, as you would see. So RuCl3 was easiest. We use a method called liquid exfoliation, which is basically a series of centrifugation and sonication, which enables you to get the 2D sheets, and this is what you are seeing RuCl3, which is Yogesh's crystal, but today our focus is on SrRu206. So here the idea, so again I will remind you that why this system is interesting. One thing is that unlike RuCl3 and Na2RO3, the Tn is very high. It is one of the rare 4D based systems with very high Tn, though it is less explored, but Tn is 550 Kelvin, which is very high, which is one good thing. Then you have lot of tunability in terms of doping, like you can, so now we have also done both electron doping, hole doping, strain, I mean we have played with SR layers as well as with RU this thing. So in addition, and then you can dilute the system. So all these possibilities are there. So in a way you can putting your antiferromagnetic hexagon under strain is one of the very interesting game which you can play, and therefore we tried this liquid exfoliation. So you can see the results, the SEM sheets for these systems, and these are the AFM measurements which says that 2 to 5 monolayers we could exfoliate in this system. And these are some of the TEM results showing the nicely exfoliated sheets. Actually, sheets exfoliated in the many of the sheets, as you can see in the first graph where you so basically this is a liquid exfoliation method, and the refined sheets float in a liquid which in this case is ethanol, and when you drop cast you get the sheet on a substrate, and then you get number of sheets. So you get lot of sheets in the shape of hexagon, which is like cleanly exfoliated, I would say. So we found this. So now we have opportunity to do measurements on sheets with varying thickness. So this is what is our next goal, hopefully, that we should be able to do measurements on the bulk limit and then systematically downscale to 2D limit. It is really non-trivial to measure magnetization in such a system, but hopefully one day we will be able to achieve it, Yogesh. And yeah, so this is finally my conclusion. We have come from this bulk hexagonal nice looking crystal to corresponding 2D sheets, and we found that thermal fluctuation induced tunneling appears to be a very good model for this system, and this also points towards the very intriguing possibility of tunneling through conducting RU planes through insulating SR layers. And we have realized the 2D sheets with various thickness experimentally, and we are exploring strain effects through doping, which is ongoing, and magnetoresistance measurement and so on. So yeah, so this work was initiated by my master's students, Suvidya and Bharat, and later Azad is continuing this work. So he has made he has doped this antiferromagnet with all possibilities which we have, including calcium, lithium, and yttrium, and so on. And this is what he is doing. And yeah, hopefully we would start our exfoliation again. And yeah.
Question?
How does the magnetism change with doping of a non-magnetic entity?
So non-magnetic, so we have even with lithium doping, which is basically lithium and calcium are doing strain. So you are basically playing with the octahedra around the magnetic atom, and still magnetism change significantly in this.
Lithium would also lead to a change of valence, right?
Yeah, so hole doped. So we have done hole doped, electron doped with lithium and yttrium. With calcium itself, where the valence will not change, with calcium itself we saw a lot of change in magnetism. Basically this is an antiferromagnet, but a loop seems to be opening up, and still it remains after that antiferromagnet. So in this
But the TN?
in calcium doped system we could do neutron diffraction, and TN remained the same even though a big loop opened. So yeah.
Can I? Very nice talk.
Okay.
I have many questions, but now I think I will ask one or two only.
Okay.
Later on I will ask more. So one question, you mentioned about SR being insulating. Do you mean SR or SR
that is a bit of a loose statement. What I meant is that in SR RU206, the conduction and valence band near the Fermi level, it is RU and O bands. SR bands are much away. That is what I. So, but since we were considering this thermal fluctuation induced tunneling conductance, which is as relatively unexplored model as the system itself is, SR-RU206. So I had to tell this that that model is suitable for conducting grains. separated by either insulator or vacuum, whatever you say, so that tunneling could happen. So that's what I meant, yeah.
And other question I had is about the magnetoresistance, what effect of magnetic field, which you mentioned later on that it's yet to be done. The structurality is hexagonal. So I was wondering, SRRU03,
Yeah.
is there any connection? Because to me it looks like SR deficient SRRU03. Can it be?
So I also thought about this question, but that system appears to be very different. If you talk magnetically, this system is really different. So the antiferrometric transition at 550 K is very subtle, and in the so in neutron diffraction you see that there is an antiferrometric transition, but when you do magnetization, you have in the Curie-Weiss region you have susceptibility actually increasing. You don't have magnetization decreasing with temperature. You have it increasing, and you have a field dependence there. So this single ion anisotropy physics is playing a role here. That's what I feel is strikingly different from other systems which I have come across. It has a different, SOC is large but not as large. It would not be like your K-type systems. But single ion anisotropy, spin orbit coupling that exists beyond TN is what is, this system is giving all indications. So yeah.
Oh, thank you. Very nice talk. I was wondering, since you mentioned the conductivity in a material that is predominantly thought of as local movement like an insulating, do you worry about whether these thermally induced conducting channels can actually screen the local moments and reduce the moment size?
That happens actually. So it is supposed to be 3 mu beta, but it is 1.38 mu beta. So this, what you are saying, is a plausible reason. Regarding insulating, it's a low band gap semiconductor. So in principle, insulator and semiconductor, and this is a low band gap semiconductor, but experimentally you even find lower. So as I said that my conclusion is that there is this band gap which is say 4 to 500 milli electron volts, but then there are defect states where hopping could take place. So a very good quality single crystal we tried to make, but with high pressure synthesis in Japan, but they couldn't form. So this is the best we can have to get a crystallite.
If you were to take the proposal of screening them seriously, then because these are thermally excited, there would be a temperature dependence in the reduction of the Curie-Weiss moment.
Yeah.
Do you see this reduction in temp as a function of temperature?
So not reduction, so because it is not fitting to Curie-Weiss law, we couldn't get the effective movement. But since it is for all other system, I could see linearly increasing magnetization as a function of temperature at a given magnetic field. In this case, it is increasing actually. That's what I am trying to tell. It is increasing as a function of temperature in the paramagnetic region. It's a very strange system. So we could discuss later, yeah.
So let's thank
Good evening, everyone. I'm Vishal Maurya. I'm a research associate in CSIR NPL lab, New Delhi, and today I'm here to talk about importance of vapor cells and how to manufacture in our own country. So you can see this is a vapor cell, and before that we have to import it from Hello. It's okay. So before that we start, I would like to know what are the vapor cells. Just a minute. Okay. Vapor cells are rubidium atom or cesium atom trapped in either quartz or borosilicate capsule, or you can say that cell and they are used for various. They are used in various applications for like quantum sensors and alkali atom and atomic clocks and gyroscope. So I think we all are familiar with the concept of atomic clocks, where you take rubidium or cesium atoms in an enclosure and shine a light, laser light of a particular frequency, and it goes into hyperfine states, and the separation between these two states is very fixed, and then you put them into a microwave environment, and they resonance with the microwave, and that gives you the particular frequency in the form of the hertz, and then you can determine the time in a very precise way, because it has a transition line with the 8.63 and so on gigahertz. So these are all used in for satellites and anything which has flight path, to determine flight path in projectiles, and atomic clocks and cold atoms, and in quantum navigations, atomic radar, which are going to be based upon those things. So this comes in various shapes, like it's spherical, and you can see that the two side windows. The
10-minute talk. I think you have to rest.
it's just only 8 slides. So and they come in the micrometer range. Okay, so how do we prepare it? So suppose you have to enclose some alkali atoms in a very tiny space with glass, and you have to first make ultra high vacuum, and then we know that ultra high vacuum doesn't work with these rubber seals. So you have to somehow connect a metal to the borosilicate or the quartz. So that's the most challenging part. So what we do is you can see that part here. So this is not available in India, and we have to actually import it, but now we are considering to make it in India. But all these things, we get this thing, and then you can attach anything with this. It can be shaped like this or that, or whatever shape the cell you want, paper cell you want. So this is the first step, and then you attach it with some vacuum system, very ultra high, 10 to the minus 8 to 10 to the minus 9 millibar, and then you can think about trapping the rubidium ion in here. Okay, so I think this is the second slide. Actually, I explained the third slide first. So what is happening is we shine a laser light through a vapor cell which has rubidium vapor cells, and we check the excitations, and then it goes into the hyperfine structures, and then according to what we are going to use, we use this excited states to sense either electromagnetic waves or to use it as a clock or whatever we want to do. But the basic idea is that you shine a laser of 780 nanometer, and this rubidium atoms goes to a hyper state, and then they trap in a dark state, and all these atoms are in a coherence state of all the up spins type of. So if a magnetic field, if a very tiny magnetic field hit it, so it will start the Lama precision, and that will change your laser lights properties, and then you can detect a very tiny magnetic field or electric field can be detected by these things. So we were trying to make this in our lab, and so this is the system where we make it. So we have a 6-way chamber, and at one part you can see that here, this is a copper tube. We put the rubidium atoms, and then we create a temperature gradient so that these rubidium atoms get vaporized, and then they travel it to the vapor cell, which I have shown earlier. So they this part is actually covered by tape, But when we are trapping this, we remove the tape, heating tape, and put this into the either the liquid nitrogen or in a chiller. So this rubidium atom flows from here and then sit here. Then we have to do the propane and oxygen gas pinching, and then we can take out this rubidium cell, and this we can use further. So this is the first time in India we are doing it, and before that we have to purchase this one cell, which costs like $500 per cell. But with this method, Make in India method, we can produce like less than $100. So these are the cells produced in lab, and we have made these cells, and you can see these SAS spectra. You can see these lamb dips here. So that means when a laser intersects the rubidium atoms, it excites into hyperfine states. So what happens is, since in the cell, rubidium atoms are moving left and right and all those places, but what we do is we send a laser that's called a probe laser, and then we reflected the same laser again, and then we intersect both lasers, and then only those atoms who are at zero speed with since the speed of since the rubidium atoms are at different speeds, they see a Doppler shift. I mean, they see the different frequencies. They don't see the single frequency. So that's why we shine a laser and then reflect it back, so that the atoms which only are at very with zero respected speed with the laser, they can only sense that, and that gives a dip, because all of the rubidium atoms are in higher state, and then there is no more to excite. So that's why we can see the dips here. This is called lamb dips, and this means this.
Because I think you don't have much time. I think you don't.
Yeah, this is final actually. So this is the crux of the talk, that we have finally able to produce these vapor atom cells, which can be used in many places, which we are trying to develop next. So our future goal is to develop RF and microwave sensing, and we want to go for the micro size of the cell, and then electric field sensing, and we are also filing a patent. So this is basically an engineering job rather than scientific job, but I want to say that this is happening first time in India, and we have used all the indigenous techniques making it. Thank you.
So,
Yeah, question.
You also make glass to metal seal yourself?
Yes, so there are three types of materials: borosilicate, pyrex, and quartz. So we use ourselves. Yeah, we do it use
how
ourselves.
you metal to these connection, how you make?
Yeah, that's the problem actually. That's we still finding out. But we so what we do is,
Wilson seal?
no, Wilson seal cannot be used, because we have to go to 10 to the power minus 8 minus 9, and Wilson seal is stopped working
Double
actually. Yeah, double stir we also tried, but it's not as effective because we have to heat it. So the
How did you make glass to metal seal?
Oh, that's a problematic thing. That's the only thing we cannot make right now, but we are trying to work for it. And all of these things, all of other things, these are all made in lab. Everything we make ourselves.
Okay, thank you.
Okay, thank you.
Once again, thank you.
Because that's the only thing which we get from Germany or China, or there's no
Kunal
other.
Yadav.
Good evening, everyone. My name is Kunal Yadav. I am a PhD student from School of Physical Sciences, Jawaharlal Nehru University. So I am discussing about a simple but a debated question, that is NBSE2 truly a multi-band superconductor or not? So this will be outline of my talk. First we discuss about the NBSE2, and then why we choose NBSES as a you can say a sample. So then we will discuss about the experiment evidences, and then conclude the talk. So the first thing is NBSE2. So NBSE2 is a well-known layered superconductor, which superconducting transition temperature is 7.2 Kelvin, and it also exhibits CDW ordering at 33 Kelvin. But the thing is, the debate is like some papers that RPS and thermal transport supports the multi Fermi surface dependency, which shows that it is a multi-band superconductor. Other measurements like STM based interpretation shows that it is a strong anisotropic single band superconductor. So the main culprit is CDW, because some the papers that claim it is an isotropic S-wave superconductor shows that the CDW mimics it. CDW reconstructs the Fermi surface, and it mimics like a multiband superconductor. So NBSE2 is itself confused. Am I multiband or single band? So the strategy is clear that we have to remove the long range CDW ordering while retaining the layered NBSE NB layered electronic platform. So we randomly substitute selenium with sulfur, where random substitution suppress the coherence required for the long CDW ordering. So the thing is, we are using sulfur, which is also isovalent to the selenium. So we are protecting the valency and the layered structure of 2H, layered 2H structure. So also the equimolar composition, that NBSES is strongest disordered point where CDW can be suppressed in the best way. So also this is a very important point, like the superconductivity here is mainly mainly dominated by NB deed orbitals. So we come to the experimental evidences. We have made the single crystals of NBSES and do the single crystal of NBSES, and we have done the XRD, powder XRD on the NBSES, and we find that the structure is almost retained, and the structure is P63 bar MMC, which is number 194. This means that sulfur and selenium has 50% occupancy here, and also the EDEX shows the weightage of selenium and sulfur is around the 50-50. Okay. Then we proceed to the transport analysis. We see here that the TC is 6.3, and also there is no CDW here in the resistivity from 0 to room temperature, and this shows that there is a no CDW ordering. And also we have fit the HC2 data with single band and two band fittings, and the single band is not well fitted with the data due to the pronounced HC2 curve at higher temperatures. So a two band Usadel model give a very good fitting with large diffusivity imbalance, which is 6.17 and 7.885. This is important. I will tell you why. Because this is Usadel model that is used to determine the dirty two band superconductor. This eta greater than 1 strongly indicates that it is a strong unequal band diffusivity. This means that this is a multi-band superconductor, and it has like you can say that it has two different bands. Either they can contribute, they can interact in intraband or interband. So the interband connectivity here, lambda 1-2 or lambda 2-1, is less than the intraband connectivity, interaction, you can say interaction. This means this is a two band model, but the interband is lower in the strength is lower. This means that the intraband connected with the interband contribution, which means it has a single TC there. So now we come to the magnetic measurements. The magnetic measurement shows like it is a bulk diamagnetic transition at 5.9, and it shows a S plus S wave fitting in the lower temperature range. So it also shows the two-band superconductivity in NBSES. Then this is the fitting, superfluid density fitting. We have done the fitting by using superfluid model. And then we have done the penetration depth measurement. The penetration depth measurement also indicates that it is a S wave, that is a, you can say like it is a fully gapped superconductor, but it is not a conventional fully wave superconductor because the value is for a S wave conventional S wave superconductor, the value should be 3.53, but the fitting shows that the value is 4.08. Then we have done the measurement using the superfluid density, using the penetration depth measurement, which shows it is a S plus S wave superconductor, which means it is a multiband superconductor. Then we have done the specific heat measurements. The specific heat measurements also shows that it is a bulk superconductor, and the gamma means the gamma shows two different regimes with a linear fitting. You can say that in the red and green data, which shows it has two different conventional S wave regime. So we can say this is the all four probe converse, which say the same picture, that all the four measurements are different, but the results is almost same. We can see here the energy from the HC1 parallel to AB and perpendicular to AB with tunnel diode oscillator technique, and the specific heat shows the almost equal energy gaps, and the weightage is also almost same, which shows it is a it is a multiband superconductor. And there is no long range CDW, which shows that this is not due to the mimicry of CDW here. The intrinsic superconductivity, the multiband is intrinsic property of the NBSE 2 - X SX range. So this is the conclusion, that 2NBSES is a multiband fully gapped superconductor with dirty limits. First, we have removed the CDW. The random substitution of sulfur and selenium removes the CDW there, and then the two-band fitting in HC2 shows multiband superconductivity, also with three different measurements of HC1, superfluid density of superfluid density of tunnel diode oscillator, and the specific heat also agree with the multiband superconductivity NBSE2. So it's the NBSES says that got it, we all are multiband. In fact, the all NBSE2 to NBSES, the whole series is a multiband superconductor. It is not due to a mimicry of CDW there. So these are, I acknowledge the JNU, Sivnada. We have done the measurement of specific heat from Sivnada University and the CSIR for. Thank you.
Okay. So, quick question. Go to empty
Yeah.
data.
Yeah.
Back. Empty.
Yes.
Why FC is positive? It look like positive.
Yes. It is. It can be due to some pinning centers in NBSES.
Okay. What is SC2 for this one?
Its SC2 is. I mean, its HC2 cross the Pauli limit. It is around 14.7 Tesla.
Should not FC should not look like that. So that is the doubt. You check that. Because if SC2 is 20 Tesla, that FC should not go. Because how much field you applied? 10 or 20 times?
No. We applied an 8 Tesla field there.
No, like there, like empty data.
So empty data. Okay.
Yeah, it is a 10 hosted.
10 was it.
So maybe like you have remnant.
Okay. I think it is not remnant, because you can say here on also in MH loop that there is some that opening in MH loop at the higher fields. This shows.
That's fine. It is a 10 hosted. Why it is going positive? Because SC2 is very high. Pinning will not make it positive. So you have to check that.
Okay. This is not a volume fraction. a volume fraction
So
of
your
4 pi chi.
conclusion,
And
so your conclusion is that charge density wave is not responsible for
Yes, yeah.
multiband.
yes.
But why you thought that it should?
There are some papers in science that shows they claim that the CDW is mimicking the multiband superconductivity type, the multiband. You can say the signatures of multiband in NBSC.
30 Kelvin, 40 Kelvin, CDW, and how it is affecting the multiband superconductor. Okay, we can discuss.
Yeah,
Okay,
yeah,
thanks.
sure. Okay.